So the next one is Paul McClarty. Paul, are you there? Switch on the sharing, please.
Great.
Okay. It's great having you, Paul. The title of the talk is Altermagnetism from a Symmetry Perspective. Paul McClarty from Paris. Please go ahead.
Okay, so thanks very much to everyone involved in organizing this meeting. It's a pleasure to be attending, and thanks also for giving me the opportunity to present this work. So the idea here is to introduce or reintroduce, I should say, altermagnetism now from a purely symmetry perspective, so a phenomenological perspective. Or more precisely, what I want to do is discuss how to write down Landau theories for these kinds of phases of matter. So this is work that's based on this paper from me and Jeff, who's at the University of Windsor in Ontario. And there's some follow-up work that we posted late last year that generalizes very much the work that we have in this original paper to all collinear altermagnetic systems. This is work with also with Judith Romhamyi at UC Irvine and her excellent PhD student, Hannah Schiff. I'll also mention in passing some other works on neutrons, also with Arsen Gukosov, who's here, and then some work on tight binding models with the people you can see listed in the bottom right. Okay, so this is the short outline. I just want to make a kind of general point about approximate symmetries and their importance in physics as a whole, and then focus on altermagnetism and its phenomenology. And then I'm going to give a more microscopic perspective, trying to write down models that make altermagnetism as simple as possible, that really just grounded in symmetries. So once you know the symmetries, it's straightforward to write down these models. And since everything is determined by symmetry, then we should see everything in the magnetic degrees, all magnetic degrees of freedom, including magnons. Okay, so I just want to make a very broad point here. It was certainly discussed in the previous talk, but I just want to give a slightly different perspective. We're all familiar with separations of scales in physics, cases where some large energy scale is determining the physics, where the physics is pristine and where it's broken by some perturbations that break those symmetries. There are lots of examples all over physics. One I'll mention here. It's a little far out, but I'll give you a condensed matter perspective in a moment. So the idea is just to focus on the lightest meson octet, the kaons and pions here. Among these, there are particles that have masses much smaller than the QCD scale. So the pions are around 100 MeV, several times smaller than the QCD scale. And you might just chalk this up to some kind of accident of nature. And you would be perfectly fine to do that. But then you would lose some important physics, underlying physics. And in particular, that's the presence of an approximate symmetry in your system. The approximate symmetry comes about when you switch off the masses, the bare masses of the lightest quarks, the up-down strange. Let's just focus on the lightest quarks. You switch off their bare masses. And then what you do is you look at the remaining theory, and what you'll see is that now you can mix those flavors of up-down strange. And what that means more precisely is that there's an SU3 flavor symmetry for the left and right-handed fermions. So there's a continuous symmetry, and we're all used to continuous symmetries being spontaneously broken at low energies. That's what happens in this case. And when you spontaneously break a continuous symmetry, there are Goldstone modes. If you count the number of Goldstone modes in this case, you'll find 8 of them. And those 8 Goldstone modes correspond to the particles in this octet. Now, these particles are not massless, and that's because the symmetry is broken, and it's broken on the scale of the bare masses, which for the up and down quarks is rather small compared to the QCD scale. So what you find is an explanation for why some of these particles have a significantly smaller mass than the QCD scale. They want to be Goldstone bosons, but they're not Goldstone bosons because the symmetry is weakly broken. But you wouldn't understand this unless you identified the underlying symmetry in the system. There are condensed matter analogs of this. In fact, in condensed matter, we don't expect really there to be any symmetries at all, only approximate ones. And those approximate ones are extremely important to us, as we know from altermagnetism. Let me give you an example in condensed matter that's tied to the previous one. These are, the pictures here show spin wave modes, magnons, in cobalt titanate, which is an antiferromagnet. It's actually an easy plane antiferromagnet. And if you look at the modes, you'll see that there are several branches, but there's a V-shaped mode at low energies. This V-shaped mode looks a lot like a Goldstone mode. It looks like it should touch 0 energy when you come down to the Bragg point here, magnetic Bragg point. But actually, if you look more closely, go in with lower incident energy with the neutrons, what you'll find is that there's actually a small gap. The gap is around 1 MeV compared to a 12 MeV bandwidth for the magnons. So what's going on here is actually a direct analog of the QCD example. In the QCD example, we had light particles coming from some approximate symmetry. And here we have a nearly 0 energy mode that's coming about because there's approximate U1 symmetry. So there's an easy plane rotational symmetry for the moments, which is weakly broken by perturbations that come from spin-orbit coupled exchange or some other effects beyond the U1 symmetric Hamiltonian. This is something that is really ubiquitous in condensed matter physics. And this is the limit that I want to focus on, one where there is an approximate U1 in the system. This U1 symmetry carries some very nice properties. If I have U1 rotational symmetry for the moments, that way I can define a spin projection SZ for, say, electronic bands or anything else you could care to mention in the magnetic sector. So that's the limit I'm going to focus on. Now, all materials have some degree of spin-orbit coupling, but it's useful to look at the pristine limit. That is the limit where altermagnetism is most cleanly defined. And then in real materials, where this is broken, you can expect there to be many materials where the spin-orbit coupled regime is actually a small perturbation to the dominant exchange split altermagnetic physics. From a theoretical perspective, what we have here is just Heisenberg couplings in the 0 spin-orbit coupling limit that turn into more complicated couplings when you switch on spin-orbit coupling. An example is given at the bottom of the slide of some typical exchange, localized exchange model when you have full spin-orbit coupled interactions. The first two terms have the approximate U1, have a U1 symmetry, I should say, and the last two terms break this symmetry. Okay, so you can expect that these approximate symmetries affect things like pseudo-Goldstone modes, as I just mentioned, but they also generate altermagnetism, and this will have effects on band structure, topology, response functions, and everything else. Now, Hyrule gave a fantastic introduction to the subject. What we want to do is explain from a Landau theory perspective the origin and phenomenology of altermagnets. So these things that in the pristine 0 spin-orbit coupling limit have spin split band structures that are anisotropic in momentum space, although the magnetism is entirely compensated and collinear. So how are we going to do this? First of all, we need to identify some local order parameter, and the natural local order parameter is just the Néel order parameter, so just the staggered magnetization in these collinear systems. And what I'm going to do is just focus on the, shall we say, canonical example of a rutile. So let's say ruthenium dioxide or manganese difluoride. So here we have a two sublattice system. There, the staggered magnetization is just the difference between the magnetizations on the two sublattices. Now, in Because we want to work in the pristine zero spin orbit coupled limit so that the ordered phase has an exact U1 symmetry, what we're going to do is keep the Néel order parameter spin symmetric in everything that we do coming from the paramagnetic phase, which is what we want to do in the Landau theory. So we have a local order parameter that this staggered magnetization N, and I want to keep everything spin symmetric. So the thermodynamic potential is just going to take this form at first sight. So there's going to be quadratic and quartic terms in the order parameter. And of course, this then captures the origin of now a collinear phase when you switch the sign of A2 with A4 positive that has now an exact U1 symmetry. So this picture here, this schematic of the double well potential is really just a cut through a higher dimensional space where everything has been symmetric. Okay, so far there's really nothing at all to distinguish altermagnets from any collinear antiferromagnet. The way to do that is to look more closely at how N is actually transforming under the lattice symmetries. In the case of the rutile, what you have is this kind of situation here. Moments living on the moments that live on their own on a body-centered tetragonal lattice. And in that lattice, you have this magnetic ordering pattern with downspins at the corners and upspins at the centers. But this is not the full story. And actually, very importantly, there is decoration coming from, say, the oxygens in ruthenium dioxide. And this decoration has the following pattern where you have this diagonal with the oxygens and the anti-diagonal with the oxygens at the half-half-half position, around the half-half-half position. So when you look to see how N transforms at zero spin orbit coupling, you see that it actually transforms non-trivially because there's a sign change when you do a C4 operation. That's all I'm saying when I say that it transforms non-trivially, but more precisely, it's actually a B2G irrep under the point group of the lattice, which is D4H or for crystallographers 4/MMM. So this actually is enough to characterize altermagnetism. And you can use this to classify altermagnets if you wish. This is what we did in our most recent paper. You just look for lattices such that the point group has a series of one-dimensional irreps, and you choose the one-dimensional irreps which correspond to collinear magnetic order that are non-trivial, so not the A1G. This is one such example. Okay, so we're not done yet. So far, there's no physics. All we've done is classify the order. So what we want to do is see how to embellish this with actual physics. And to do that, what we're going to need to do is take the original Landau philosophy and ask what things can couple to one another such that the thermodynamic potential, such that you can include them in the potential. In other words, they should be universal invariants. So let's look at this object here. This is some kind of multipolar operator. It's symmetric in spin space. This is, if you like, the local magnetization density. I'm keeping everything spin symmetric, so I'm not exposing the components. And what I'm doing is projecting out the R-mu symmetric part, so rank 2 symmetric part. Overall, this has 3 components. So it's an octopole, but it's time reversal odd. So I'm going to call it the magnetic octopole. That's the standard terminology. And I'm going to focus on the XY component. The XY component has the same symmetry as N. It's this B2G irrep. And so what that means is that in the Landau theory, there's a term allowed that just linearly couples these two things. Okay. You might call this a secondary order parameter. This is a slight abuse of notation, pseudo-primary more precisely because it has the same symmetry as N. It has the same symmetry, but it exposes different physics. So if you rotate 90 degrees in momentum space or in real space, this object here flips sign. So in order to preserve the sign of the order parameter, the magnetization has to switch sign too. In other words, this is a D-wave object in the magnetization or in the band structure. So you can directly read off the altermagnetic nature from the coupling to some kind of magnetic multipole, in this case, a D-wave one. Now, another thing about this Landau theory is that it directly tells you about the spontaneously broken symmetry. In particular, there's a residual SO2 as soon as, or U1 symmetry as I go into the magnetically ordered phase. Now, these magnetic octopoles can be used as a tool to see what kind of spin splitting there is in the band structure, but they should have a life of their own as well. This was originally pointed out, I think, by Boval and Spalding in this paper, where they carried out first principles calculations on the relative of ruthenium dioxide, manganese difluoride. This is now an insulator, and what they noticed is that there are these objects which they precisely characterize as magnetic multipoles, and they suggest ways in which they can be detected, in particular using magnetic Compton scattering. They should also be visible in elastic neutron scattering by looking at the form factor at high momentum. So the Landau theory also tells you about the residual symmetries in the spin in the ordered phase. So, for example, there's this U1 that I mentioned several times. There's also another spin operation where you perform time reversal and bring it back through a C2 perpendicular to the moment in spin space only. But the group that multiplies this is also non-trivial. It's not a simple magnetic group. As was mentioned in the previous talk, one has to think of spin groups, a generalization of the magnetic groups in the ordered phase. So in particular, rather than having a C4 that's in both real and spin space, here you decorate it with, say, a time reversal operation, or by operating with this, by a C2 in spin space. So what we have are these operations that generalize the ordinary magnetic operations that have different, that may have different spin and space transformations. These were originally observed in the 1960s by these people, maybe among others. There was a long hiatus where these were little studied, and this sprang back through different contexts more recently, and has now led to a discussion of the representation theory for the spin point groups, as well as enumeration of a partial enumeration, because there's in some sense an infinite number of the spin space groups. So now let me give you a slightly different perspective, a more microscopic perspective on the physics. So what I want to do is take the rutile example, and I just want to focus on writing down a very minimal model using the symmetries that we just discussed. I want to preserve zero spin orbit coupling, and I'm going to work with the rutile example, though any example will do. One of the amusing things about this example is that it shows up some other physics that I'll very briefly mention. So what I'm going to do is just forget all of the correlation physics and just think about electrons, non-interacting electrons, hopping on some lattice, this rutile thing. And I'm going to have them hop only between the magnetic ions. And in order to incorporate the magnetism, I'm going to do that very minimally through a Hund coupling like this. So there's an on-site interaction that's spin symmetric that couples the electronic moments to the spin moments. And the spins are just going to be considered frozen. They're just classical moments pinned in the magnetic directions here. And then the only thing that I have at my disposal is to think about the hoppings. Turns out that if I switch on just the minimal hopping between the different magnetic sublattices, the band structure is completely spin degenerate. And that's because this model, even though I'm enforcing all of the lattice symmetries, thinks that it lives on a different lattice. It thinks that it lives on a body-centered tetragonal lattice. The same is true if I switch on that hopping, the diagonal hopping here. The symmetry is only broken down to that of the lattice when I switch on this hopping here. This hopping is not equivalent to this hopping because there's no C4 symmetry. There's a C4 translation symmetry, so that one is equivalent to the one originating from this one along 90-degree rotated to this. So actually, at the same range, there are two different hoppings or two different colors, and those hoppings are essential to break down the symmetry. This model has a spin symmetry too, so the 4x4 Hamiltonian is block diagonal, 2x2. And because you have these two different colors for the hoppings, now you can think of the band structure as just squashed along the 110 direction like this, and the opposite spin is squashed along the opposite direction, so along the 11 bar 0 direction. And that leads to this spin split band structure with a D-wave pattern, purely from symmetry with a very simple microscopic model. That's altermagnetism from a non-interacting perspective. I'm just going to digress for a moment, just 2 minutes or 1 minute even. I just want to say that the phenomenon of hoppings, S-wave hoppings, having higher symmetry than you impose at the beginning is actually extremely common. So this rutile example has higher symmetry hoppings all the way out to 7th neighbor. And it turns out that there's a lot of rich structure to this. So an example here that's not rutile is Kagome. If you just impose a C6 symmetry, it turns out that these 3rd neighbor couplings have come in 2 different colors that break down the symmetry to C6, whereas the shorter range couplings like this one have a higher symmetry. It turns out that there's a hierarchy of different symmetries that one can have. You select your parent symmetry at the beginning, and the model may have a whole sequence of symmetries corresponding to either the eigensymmetry, so which is just the symmetry of the points in space between which you're hopping, and the subgroups connecting down to the parent symmetry group. This is discussed in work from last year. For altermagnetism, this is interesting because we have a lookup table that tells you precisely which Heisenberg coupling or S-wave hopping you need to switch on in order to break down the symmetries to obtain an altermagnetic band structure, which may be useful to some people. Let me come back to Landau theory. I told you about the rutile example, but it generalizes. So for example, we always want to find some kind of order parameter that's time odd, spin symmetric, spatially anisotropic. Manganese telluride, it's this rank 5 object here, and this rank 5 object tells you directly that there's a G-wave splitting, which, as was mentioned in the previous talk, has been seen using spin polarized R pairs in manganese telluride. Now, so far I've discussed Landau theory at 0 spin-orbit coupling. This is the non-standard case. The completely standard case is where you have finite spin-orbit coupling. And of course, one can do standard calculations that tell you useful things for experiments. For example, when you switch on spin-orbit coupling in the rutile case, it's straightforward to show that there's weak ferromagnetism. In other words, there's a coupling between the nail vector and the magnetization, which looks like this. Turns out it looks like this. Because there's weak ferromagnetism, and the magnetization transforms in the same way as the sigma xy component of the anomalous Hall effect. This means that when you switch on spin-orbit coupling, there's also an anomalous Hall signal. This is very common across the altermagnets, whether at linear order or higher order. So this is just the standard analysis, and extremely important to do this kind of analysis when you're interested in the observable signatures of altermagnetism. But for us, one of the most interesting questions was, if you know what happens in the pristine 0 spin-orbit coupling case, can you say something concrete about the finite spin-orbit coupling? In other words, can you match the 0 spin-orbit coupled Landau theory to the finite spin-orbit coupled Landau theory? The answer is yes. And just to give you a taster of what this kind of statements look like, one can show that in the rutile, so for the rutile symmetries, I should say, when you have linear coupling to a magnetic octopole, when you switch on in the 0 spin-orbit coupling limit, when you switch on spin-orbit coupling, there is weak ferromagnetism and an anomalous Hall effect at the linear level. Okay, so this is the kind of matching condition which we've now turned into a general statement that you can apply to any altermagnetic system. Coming back to yes,
Paul, you have maybe 1 minute, 1.5 minutes left.
Okay, good. So I'll wrap up quickly. So I just want to advertise that this kind of physics can be generalized to rutile systems, to manganese difluoride, where rather than at the linear level, you find cubic couplings to the anomalous Hall effect. And all of this physics carries over to magnons. So in magnons, magnetic excitations, we expect that the symmetries are dictating physics that is purely altermagnetic. In this case, rather than spin splitting, what you find is chirality splitting. And similar games can be played. So you have a rutile structure, and now it's the Heisenberg coupling that connects these anti-diagonal bonds that splits the band structure, now not in spin, but in chirality, in a D-wave pattern. And as a final remark, I'll just say that you can observe, we've shown that you can observe the characteristic signatures of altermagnetism in the magnons, so directly in the magnetic degrees of freedom, by carrying out polarized neutron scattering, where you're sensitive to these cross terms. It was shown a long time ago that if you send an unpolarized neutron beam into a ferromagnet, it gets polarized. In a classic antiferromagnet, it doesn't get polarized. We know that altermagnets mix signatures of ferromagnets and antiferromagnets. And what that means for the case of neutron polarization is that if you send in an unpolarized beam, it gets polarized, but in a D-wave pattern, which is a direct experimental signature of altermagnetism from the magnons. So with that, I'll wrap up and take questions. Thank you.
Thank you very much, Paul. So before going to questions in the room, let me go to Olena, to Helen Gomanai. Please, Helen.
I am here. Oh, okay.
Hi.
Hello.
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 Hello. I have a question or comment to your talk. So can you go to the slide where you show this definition of your order parameter, like for rutile? Yeah. Yeah. So here, for me, the problem is that to calculate this order parameter, you need to know already the distribution of your magnetization. So how would you introduce this order parameter in a paramagnetic phase where you do not have any magnetic density at all? So this is the point of the Landau theory. You start from the non-ordered paramagnetic phase and then go down through that transition point, taking into account all the magnetic fluctuations. So with this order parameter, I have a problem. What is M in your notations, and how do you define it?
Yeah, so M, as I said, is the local magnetization density. I think I could rephrase your question and ask something similar just for the Néel order parameter. This is just the difference between magnetizations on the sublattices. This is 0 in the paramagnetic phase. When I go into the ordered phase, then there's a vacuum expectation value for the magnetizations on the sites. Now, the same is true for this object. This acquires finite vacuum expectation value once you go into the ordered phase. Does that answer your question?
No, because according to the Néel approach, we have not only the Néel order parameter, we have also magnetization. So I know in the classical picture, I know exactly what the sublattice magnetization means. Yeah, so I can trace it up to the Néel point or the like behavior of it using the statistical physics in the vicinity of the Néel point. And then I have two sublattices. So I have a Néel vector and I have a sum, so a macroscopic magnetization. Then this MR is something which appears on top of this. So how can I imagine what is this? Is it different from sublattice magnetization, M1 plus M2, and so on? Because it's important in the Zeloshinsky picture. Yeah, you showed also it below. You are dealing only with N and M, which are correlated with the macroscopic sublattices. And here something appears which I cannot associate either with the electronic spin and so on. Can you comment more on this?
Yes, so as you point out, this is directly related to the electronic spin density in the unit cell, from which if you had the magnetization density, sorry, this local magnetization on its own, then you could, of course, compute from it the leading order multipoles, which are just the local sublattice magnetization, and hence the Néel order parameter. It turns out that in this rutile system, these point-like objects are not enough to specify the symmetry on their own. you need to have some kind of extended object. And this extended object is what the multipole is trying to capture.
Okay, let me go to Cairo immediately after this, please. Cairo?
Yeah, thanks, Paul. It's just a bit of a comment because for the students, it's in terms of trying to understand. So what Paul is, I'm going to paraphrase a little bit, Paul, and you can maybe comment on that. So he's trying, we know how to do Landau theory for a long time. This is actually what Holland has done many times as well, and how to generalize this and then look for the Landau functionals. Now, some of the issues here that is coming is you're trying to sometimes use tools from the past, not from a perspective of the spin groups. And then once you have this in front of you, then you can try to build from a system that is not built for that, these type of probability parameters that will match them. I'm going to make an analogy a little bit. It's not a direct analogy, it's not fair because the Landau theory in fact is quite complete. But imagine that you're trying to describe orbital motion of the planets, but you have a geocentric type of theory, which is working very well, except for some anomalies once you actually have a system. And somebody comes with a heliocentric one that you can see that this is quite clear, but then you try to rework some of these knowing the results. So this is one of the things that in this approach, sometimes, for example, the monopoles and expansions, they are there, that's clear, because all of the reversible representations will be there by definition, but identifying really the physics and not the spin exchange physics directly, that requires the spin symmetries to begin with, as we introduced and fully classified all of the systems. But then, of course, at the phenomenological level, you still have to describe, like we did with Jerome and things like that, some of these physics for the domain walls and the magnetic sector and the magnon sector. But just so you understand that, they're not conflicting, but this, the spin symmetries really is the one that fully define things here.
Yes, I completely.
Please, yes.
Yeah, so I agree with that. So the spin symmetries are specifying these are the appropriate symmetries in the pristine altermagnetic limit in the ordered phase. And this Landau theory approach completely captures all of these spin symmetries within the ordered phase. Now, it turns out that when you approach from the paramagnetic phase, everything is also spin symmetric, but it has maximal spin symmetry. It has perfect SU2, if you like, or SO3 rotation symmetry. And it's actually that fact that allows you to skirt around having to deal with spin groups, at least at the Landau theory level. And in fact, you can just think about the permutation symmetry of the magnetic order between the sublattices.
That's exactly, you're right. I mean, this is how Landau theory is built. You have something that agrees at all levels with the paramagnetic phase, and then you decouple the order part and the other part that is still compatible, but there's many thousand billions of terms, essentially. And you need a guide to that. That's the point.
Yes.
Why do you need to couple it with the magnetization?
Okay, it's okay. Let's allow other people to ask questions. Yeah.
Okay. Let's discuss this afterwards.
Last word to Paul. Paul, you have a last word.
Okay, well, thank you. I'm not entirely sure what is the point of disagreement. So or if there is indeed any disagreement at all. Here is an object that is certainly allowed by symmetry. I think it's well defined. There is a local magnetization density coming from the electronic band structure. You could, if you were doing first principles calculations, as people have done, compute this directly. And it turns out that if you think about how this couples to the Néel order parameter, then you directly capture this spin splitting pattern coming from, that really defines altermagnetism, or is the empirical signature of altermagnetism in a pristine limit. And then, of course, you can connect this to finite spin-orbit coupling. So,
okay, thank you very much, Paul. That was a very nice talk. And thank you for the discussion also.
Thank you.